All right, let's take a look at the equation for the Doppler effect. The equation looks something like this. The frequency that is observed by an observer is related to the frequency that is created by the source by multiplying it by this big, interesting looking fraction. What we need to do first is define all these variables. FO is the frequency that is observed. Fs is the frequency generated by the source. V is the speed of the wave. This is sound we're talking about. This would be the speed of sound. If this is light, it would be the speed of light. VO, the velocity of the observer, and Vs, velocity of the source. I think the only way to properly demonstrate this is to do an example. Let's imagine we have a situation where the speed of sound is 340 meters per second, and we have an observer that is at rest and a source that is moving toward the observer at 50 meters per second. Now it looks like we also would need to know what the frequency is that is being created by the source, and I'll say it's 500 hertz. Now the way this works is I would plug these numbers in, but it's a little more complicated than that. So I'd have the speed of sound, and the observer is moving at 0. You notice I'm not putting the plus or minus in there. That's going to come next. And I have the speed of sound and the speed of the source. Okay, this is where it gets tricky. Up here, it doesn't matter whether I call it plus or minus because I'm adding or subtracting 0. But down at the bottom, I'm either going to add or subtract the 50 from the 340. And the question, of course, is how do I know? And this is where you got to use your common sense. We know from the conceptual video that if the source is moving towards the observer, the frequency that is heard will be higher. So I have to look over here at this fraction and figure out what I'm going to do on the bottom there to make that fraction come out to a number that's greater than 1. Because if I come out with a number that's greater than 1 and I multiply it by 500, I will get an answer that is greater than 500, which is what I absolutely expect to see. If this was going in the opposite direction, I'd try to make that fraction come out to a number that's less than 1 to get the opposite effect. I've got 340 on top, and I'm going to either have 340 plus or minus 50 on the bottom. If it was plus, then the number on the bottom would be bigger than the number on top, and I'd have a number less than 1. So that's not what I want to do. I want to subtract that so the number on the bottom is smaller than the number on top, so the fraction overall is greater than 1, multiplies by 500 to get my answer. Now what if instead we have the same numbers, but it's the observer who's moving towards the source? Then I would go through the same process, but this time the 50 is going to be up top. Again, since they're moving towards each other, I expect a frequency increase to be observed. And so in order to get a fraction that is greater than 1, I would add the number on top, because 390 over 340 is greater than 1. If I multiply that to 500, I will get an answer that's greater than 500, which matches what I know should happen. So you have to use your understanding of how the Doppler effect works in order to get this. If these objects were moving away, that would exactly change the sign of both of them. So for instance, if in the top one up here, they were moving away from each other, instead of moving towards each other, this would become a plus. On the one on the bottom here, if they were moving away from each other, this plus would become a minus. Now let's take a look at another idea. What happens if they're both moving? What if I have a car blaring its horn approaching another car coming in the opposite direction? And I'm just going to call this Vs and Vo. Now I'm going to do this without numbers. If I look at the generic form of the equation, how I do this is I break it down and look at the two things separately and then deal with the top and the bottom of the fraction in isolation. If the observer were moving towards the sound and the sound was sitting still, that would cause an increase in the frequency. Now, to get an increase, you want to add the two top numbers. You wanted the top number to be bigger than the bottom number. Now, if the observer were sitting still and the source was moving toward it, I would also want to increase the frequency by subtracting the numbers on bottom. So in this case where they're both moving towards each other, I'll add the top, subtract the bottom, which actually gives a bigger effect than if one of them were sitting still. And you can imagine if they're moving away from each other, you would do just the opposite. So you have to kind of use your common sense.